Yeah, I just yawned. So
This is true. All right, so... Oh, that didn't work. All right, so... Eek. Negative x squared plus 6x minus 5. I got to remember that. Y equals... do not like that. What was it? Plus 6x?
Yeah.
Minus 5. So, back in the day, we only had one choice, and that was to do it by hand. Nowadays, though, you actually have two choices depending on the directions. You can do it by hand, you can do it with your calculator. We're going to do both, and we can either do it by our calculator and hope we get the same answer by hand, or do it by hand and check it with our calculator. What do you want to do? Okay. Morgan was quicker on the draw. So, if I want to find the area enclosed by this parabola and the x-axis, I have to have an idea of what it might look like. Do you have any idea what that graph looks like? Upside down parabola. Can you be more specific?
frowny face.
It is a frowny face. So it's going to have y-intercept at negative 5. How about zeros? Can you talk to me about zeros? I think that's going to be important. 1 and 5?
Plus 1. Minus 1. No. Plus 1.
So I'm going to get negative plus.
No.
Does that work? Negative x times negative 5 is positive 5x. X times 1 is x. Add them, I get 6x. I think I did it. Yeah. So that has a x-intercept at, what, 1 and 5?
No, positive.
No, it's positive.
Oh, right.
All right. So it's going to look something like, whoa, what was that? It's going to look something like that. And so now when we say the area bounded by that graph in the x-axis, we're talking about this area, enclosed by, contained between, okay? And not only that, finding those zeros is really helpful because we just found the limits of integration, right? Okay, so I know what I'm doing is this. I'm trying to find the definite integral of negative x squared plus 6x minus 5 dx. Now that's the calculus way of writing it. We can actually evaluate it using like an algebra 2 way of writing it. And that's because we know that the definite integral of a derivative tells us exactly how much the function changes. So in other words, if I can find out how much the function changes, that's exactly what the definite integral of the derivative is. So the question is, what is this the derivative of? And since I have several qualified antidifferentiators around, you will tell me. Right? Is that okay? Don't need the plus c because it's a definite integral. Okay? So if it was an indefinite integral or an antiderivative, I need plus c. But because it's the definite integral and I'm evaluating it, I don't need the plus c because I would just add c and subtract c and they'd cancel out, which would be nice. So what this says is, hey, evaluate this function at 5 and at 1 and find the difference between them. All right, so what's that? Negative 125 thirds. Oh, yuck. Plus 25 times 3, 75, minus 25. Subtract negative 1/3 plus 3 minus 5. Plugging 1 in was a lot easier, don't you think? Okay, little mental math here. All right, I get negative 125 thirds, and then I get, what, plus 50, and then I get plus 1/3 minus 3 plus 5. You can't just multiply everything by 3, because that would get me 3 times the answer I wanted. Okay, you could times everybody by 3 and then divide everything by 3, but you can't just multiply a number by 3. It's like saying 2 is the same as 6. That wouldn't be good. 50 plus 5 is 55, minus 3 is 52. I have 52, and then 125 thirds negative plus a third would give me negative 124 thirds. Any chance that goes in evenly? You can. I mean, I'm saying it's not like, I don't think we've done anything where...
Oh, it's 41 and a third.
41 and a third? Okay. 10 and 2/3? Okay. So, do you want to, let's see. So, Arnie, yeah, you can use your calculator. I would maintain the fact that everything we've done so far, we didn't need our calculator. Certainly, it may have made the calculations or arithmetic easier, but we're all right. Do you want to ask any questions on what we did? Because now we're going to check with our calculator. Julia?
Well, are there going to be quizzes where we can't use the calculator?
I would imagine somewhere along the way, a quiz or a something where you can't use your calculator.
But once we get to the test, we can use it.
Yeah, I haven't really toyed with the idea of non-calculator parts of the test so far this year. It's not out of the realm of possibility, but you can definitely count on being able to use the calculator on at least some of the test, if not all of it. I'm not giving you a non-calculator test. Okay. In general, this year I've been trying to keep that to quizzes, so that you feel like it doesn't cost as much points to make arithmetic mistakes. Shouldn't be making them, but it doesn't cost you too much. All right. So if I now go back to my calculator, we'll go to the large screen. I think I need to be in function mode. Let's see. Yeah, we were doing pre-calc. We were doing hawks and doves, parametric equations. All right, so negative x squared plus 6x. All right, sorry, minus 5. And I'll go to Zoom Standard, I think will get me a good window. And, hey, look, our graph was right. Like, that's what we thought. It was going to have those zeros. Now, you could see that if you actually went to the graph first, it's telling you what the limits of integration are. You don't have to figure them out, right? But you can find the limits of integration by doing it by hand, and it's, not too bad. All right, so do you want to do Calc 7 or Math 9? I don't really care. Calc 7. Okay. Second Calc 7. Lower limit, 1. Upper limit, 5. Hey, what do you know? 10 and 2/3, which is exactly what we got, which makes us feel good. Is that all right? Yeah.
Is that all we have to do? Just do Calc 7?
Yeah. You want to have to do more?
No, I just thought you were like, do you want to, I thought we'd do something different.
No, so, here it is, right? In this case, the calculator did it a lot faster because we had a lot of arithmetic to do. There are some definite intervals that are actually easier to do by hand because there's not a lot of arithmetic to do. Okay? I'll give you this example and you may not agree with me. But if I were to do that definite integral, the antiderivative of cosine is sine, and evaluate it between 0 and pi. I know that the sine of 0 is... Sorry, I did it backwards. The sine of pi is 0, and the sine of 0 is 0. So the answer would be 0. So if I were to look at cosine x from 0 to pi, we would expect the definite integral to be 0. I did that because I know my trig. Some of you remember your trig. Some of you don't. So if we actually did the cosine of x and we graphed it. Yep. I saw it, and let's fix that. And you can actually see, that's a bad picture. Maybe zoom decimal. That's a little better. So if I go from 0 to pi, that's about 3.14. Can you see that just visually? I do Calc 7, 0, enter, pi, enter. Hey, what do you know? Now, what did the calculator tell you the area is, or the definite interval is?
It's very, very close to 0.
Yeah, it's negative 3.21 times 10 to the negative 14th. So the calculator can't do it, but we can. Now, I'm not positive. Let me just check it out, because I've heard teachers say that Math 9 is more accurate than Calc 7. So I'm curious if I did this using Math 9 and said cosine of x for the variable x going from 0 to pi. Nope, that's e. Here's pi. Pi. Oh, no. Same thing. Wow. Interesting. So not all that more accurate. You want to ask any questions? Is that all right? All right. So if we look now at
So,
yeah, go ahead.
like for number 2, you just like find the zeros and then do like Calc 7.
Yep. Or you could do it by hand, right? Now, in this case, I just want to point out, it says find the area of the indicated region, right? So if our area is below the x-axis, we wouldn't say the area is negative 4. As a matter of fact, I should go back and say, look, if it actually asked for the area here, the area is not 0. It is. Let's actually, let's figure that out. So if I go back to this, and I'm going to do, I'm just going to clear that drawing. If I want the area from 0 to pi, I probably would, it would probably benefit me to find the area from 0 to, pi over 2, exactly. Pi over 2, and that area is 1. So the area from 0 to pi is going to be 2. Okay.
Oh, wait, if it comes up with an exact answer for...
I know, weird, don't you think? I agree. So the folks at TI, whatever algorithm they use, like, for some things it works pretty perfectly, and for other things it doesn't.
That's weird.
It is. But they won't tell you what the algorithm is, right? I mean, these are like the secret sleuth calculator people, and they don't want to let you know what they're doing, or else you might decide to build a calculator. Anyone going to do that? I didn't think so. All right, so let's see. Maybe we'll go back to 5, but right now let's do 6. And 6 is actually screaming to you, use your calculator. Okay? As a matter of fact, if you tried to find... Oh. Alright. Let me do 4, and then we'll work up to 6. The area bounded by the graph of y equals x squared and y equals x. So if I actually put in x squared, we don't need our calculator for that. That's silly. Alright, so y equals x squared, everyone says looks like?
Happy face.
Parabola y equals x. Something like that. Give me one point where they intersect. 0, 0. And give me another point where they intersect. 1, 1. So the area bounded by these two curves, or enclosed by, is that area. And we've never really done that before.
There was one problem on a homework. Nobody could get that.
Maybe there was. Maybe there was. So let me give you a strategy. What if we took the area of this triangle and then subtracted the area of that red region? You'd get the blue region, right? All right, so actually what we're doing is the area of the triangle is from 0 to 1 of y equals x. That's the area of the triangle. And we're subtracting off from 0 to 1 the area under x squared. So we're taking this whole green area, the area under y equals x, and we're subtracting this red area, the area under y equals x squared.
So, if you're going to do any calculation, could you do the y, so y 2 minus y 1?
Yep, you totally could. Okay, so look, there are a couple ways of thinking about this. We're really just looking for these rectangles in here. And Alicia's saying, well, isn't that just the height of y1? And we're subtracting off. So we're taking this whole height and we're subtracting off y2. So isn't this the height of that rectangle, y1 minus y2? And it definitely is. As a matter of fact, I can actually write it like x minus x squared from 0 to 1. I can say, hey, it's the tall function minus the small function. In this case, the tall function is the function that's above. And the small function, x squared, is the function that's below. David?
Can you just like find the area of the triangle? Like, is it one time?
Yeah. You totally can. And then subtract off the area. Like, so there are lots of ways of doing this. I'm doing it this way because when we get to 6, it's going to be a little bit harder to say, oh, that's just a triangle.
Okay.
So here's one we could actually do by hand. 1/2 x squared minus 1/3 x cubed. How'd I do? Between 0 and 1. I plug in 1 and I get 1/2 minus 1/3. I plug in 0 and I get...
0.
That's awesome. Half minus 1/3, what's that, a sixth? And then I want to show you that Alicia's thought about doing it on the calculator is actually going to do the same thing. If I do x minus x squared, and I'm going to go, I think, zoom decimal. Ooh, I can actually do better. Let's do window from 0 to 1 and from 0 to 1. And so, if I take a look, let's see. No, hold on, I'm going to try to show you. So if I do what Alicia's method, Alicia was saying, I want you to look closely at the green triangle, the green rectangles that I'm drawing. Do you see how they start off very small and they get big in the middle and they start off and they end up small? Alicia's method, the only thing different is we're still taking those rectangles, but we're just putting the rectangles on the x-axis now. So these are the same rectangles that we have up here. We're just lining them up along the x-axis. Here they weren't lined up along the x-axis. So by saying the tall function minus the small function, we get the same rectangles, but lined up along the x-axis. And now when we line them up along the x-axis, we can use our calculator. Second Calc 7. And now we can say, hey, go from 0 to 1 along the x-axis. 0.16 repeating, that's a sixth. So that area right there is exactly the same as the area here. So this area is the same as this area. Is that all right? All right, let's go to the screaming calculator question. So 6 is just begging to use your calculator. So 2e to the 0.2x. Actually, let's do 8. All right, because they don't tell us what the limits are, and I like that. So x plus cosine x. Make sure you're in the radians. All right, x plus cosine of x. And what's the other one? 2 sine of x squared or 2 sine squared x?
2 sine of x squared.
X squared. All right. And I'll start with zoom decimal, see how that works. Whoa, check that function out. Whoa!
What the?
Oh my goodness. This is nuts! Alright, so, I'm gonna grab this picture, and so, this is where that word bound comes into play. It wants the area bound or enclosed by these two functions. How many different areas are we talking about?
Just one.
I hear a lot, 1, and 4.
It's not one.
I know it's a lot.
Maybe 4.
Do we agree that that area is between?
Oh, that's 6.
Is this area between? That area is between. And the question is, maybe there's a little bit right there.
We're missing one
And
more.
then, like, if it
Not
goes-
really.
No, right underneath the one in the middle.
What?
So this area is not between the two functions. It's between the x-axis and either of the functions, right? So we just need between the two functions. Yeah, Alicia?
Because you don't know, well, from looking at the graph, you don't really know how the functions, like, end or whatever. So could you say that the area to the right and the area to the left are also there?
So that's a great point. And I actually know that this function is going to go off like this, and this function is going to keep oscillating between 1 and -1. So off to the right, all of this area is unbounded. It's just infinite amount of area. And off to the left is going to be a similar thing. But that brings up a very good point. You pretty much need to know what the functions are going to look like, because if you don't, maybe they do cross again. You know? All right, so I have I have some strategies for you. It could be 4 separate problems where, do you agree that the tall and the small functions flip-flop? So one you'd be doing y1 minus y2, and the other you might be doing y2 minus y1. So here's how your calculator might help. If we just looked at vars, y-vars, y1 minus vars, y-vars, y2, and I'm actually going to turn off my other two functions. I'm just going to look at the difference of the two functions, because that's going to be the height of the rectangles. So, look, here's all this unbounded area. Finally, here's a little bit of positive area. Here's a little bit of negative area. Here's some more positive area. And here's a teeny little bit of negative area. So, you could find the area from here to here, count it as positive. From here to here, flip the negative sign, make it positive. From here to here, make it positive. From here to here, make it positive. I have a trick. What's the trick to make all my areas positive?
Oh, plus one.
Nope. Not bad, but I have a trick. And it's not adding 1. What will make everything below the x-axis above? Absolute value is a great trick. So I can actually go down and say, hey, insert math number absolute value. And now if I look at this again, everything's above the x-axis, and the area that I want, let me go get my picture. The area that I want is all right here. And this little piece. Ooh, that's really bad penmanship. Sorry. Now, here's the trick, though. You do have to find out what that 0 is, and you have to find out what that 0 is. And can I be honest with you? I think if you try to find the zeros after you do the absolute value, I don't think the calculator will find them.
You just do calc intersect with the first graph, and then
You could do that if you didn't get the first and two graphs off of each other. I think your calculator, the algorithm it uses to find zeros, is it looks for positive values changing to negative values. But since we did the absolute value, all we have are positive values going to 0, going back to positive values. So I think you actually have to find the zeros first before you do the absolute value, and then you can do the absolute value to find area. And that's a great example of the difference between area and the definite integral. Because the question asks for area, we need it all to be positive. All right? Hey, that was a lot. You did a good job. We're going to do a couple days with finding areas, and then we're going to move on to finding volumes. So again, very mathematical kind of things. And I'm not ready yet, but at some point you can start asking, well, why would we care about finding areas? And maybe I'll have some answers for you. All right. Have a wonderful Wednesday. Get out of here.